All right, so today's lesson is going to be on distribution of matter in space. So we're going to look just basically at a bunch of different ways that all throughout the entire universe, matter has clumped in different ways to organize itself in different clusters throughout the universe. That's kind of a really broad way of spelling out what today's lesson today is going to be about, but it's a good one. So here we go. So there we go. We're going to be learning about various objects that appear throughout space today. We're going to talk about stars. We're going to talk about black holes, galaxies, and the universe as a whole. So again, that's focusing just on how matter throughout the entire universe is clumped into certain sections, whether it's stars, black holes, galaxies, or just the universe as a whole here. Awesome. Here we go. We're ready to roll. So stars, first and foremost, these are the ones you probably are most familiar with out of all the ways we clump matter in the universe. But you might not know the following bits of information. So stars are actually made of very hot, glowing gas, and the gas is mainly hydrogen gas. That's especially true of our own sun. It is mainly made of hydrogen gas. Now, they can be a wide variety of sizes and colors. It's a little bit backwards to what you might expect in terms of what their color tells you about it. Hotter stars are blue, and cooler stars are red. Now, our star, the sun, of course, is more on the red side of things. It's kind of a yellowish orange star. It actually is pretty small and cool in the grand scheme of things, right? Our star is actually really nothing special. Like, I mean, it's very special for Earth, of course. The sun is pretty much the source of all the energy that supplies life on Earth. But still, in the grand scheme of things in the entire universe, our sun is pretty insignificant. It doesn't really have a lot going on to it. But yeah, anyway, moving on. Now, how do stars work? Like, what the heck? What are they even doing, right? So a process where two hydrogen atoms combine. So if this is hydrogen here and this is hydrogen here, there's a process where these two hydrogen atoms combine together to form this big explosion, and it makes helium. And that actually occurs in the core of a star. We call this nuclear fusion. So it's where two hydrogen are just pressed together with so much force that they actually fuse together to form helium, nuclear fusion, right? This is an extremely hot process. It's about 10 million degrees Celsius. It happens right in the core of a star. And believe it or not, this is actually the exact same process that happens when some types of nuclear weapons are detonated, except on a star, of course, this is happening constantly in the core of that star, right? So if you look at the sun, if you look at any star in the night sky, what you're basically looking at is like a gigantic nuke going off at all times. That's a very simplistic definition of course, but it is kind of a cool concept to think of it that way, right? Now, when hydrogen runs low, so when the sun or any star stops having as much hydrogen left, because hydrogen is the fuel behind this reaction, the larger stars are actually large enough to take this helium and smash helium particles together to turn it into carbon, which is a little higher up on the periodic table, of course, right? So it's kind of an interesting pattern how this works. Now, in order for that to happen, helium jumping into carbon, the star has to be pretty massive. There has to be a lot of mass pushing these things together, way more than an ordinary star. So not every star is going to get to a point where it's actually fusing helium into hydrogen, or I mean helium into carbon rather. But the most basic reaction of all of them is the one I described, where we are taking hydrogen and fusing them together to form helium. Anyway, moving on. So next little topic of discussion here, this is a little bit of a sidetrack thing. It's something called the Hertzsprung-Russell diagram. You can just simplify that by calling it the HR diagram. Not a big deal, right? So an HR diagram is a way of classifying stars. They always look something like what you see right here on the right-hand side. It basically is this diagonal line with a few little branches coming off it, and then this little cloud that's kind of sitting on its own. And what this diagram shows is it's basically a model of a star's temperature, which is along the x-axis down here, compared to its luminosity, which is kind of like brightness. It's a little bit different than that. I could explain it if you want to come into the Zoom and I'll tell you the difference. We don't really need to know, but it's kind of like brightness. So yeah, that's what this is really showing. I don't like how a lot of them are set up because they're kind of backwards to what I would usually imagine. Notice along the x-axis here, the higher temperatures, like 30,000 degrees right here. Well, actually it's 30,000 Kelvin, which is related to Celsius. Just think of that as a temperature. For whatever reason, they put that on the left, and for the cooler temperatures, like 3,000, they put it on the right. I don't know why they did that. It would make a lot more sense, I think, for the cooler ones to be on the left and the warmer ones to be on the right. But whatever, it is what it is, just as long as you're reading the scale appropriately. What this kind of shows us is down here in the cooler stars, so the ones on the far right, for the most part, a cooler star has a low luminosity because it shows up in this little band right here. So there's a whole bunch of different stars that are listed. They're all very cool stars, relatively speaking, and they all have low luminosity. Now, our sun is located right here, right? Notice its luminosity is 1. That's based off of a solar unit, so it's based off of itself. And the temperature of the sun appears to be just below 6,000 Kelvin. So in the whole grand scheme of things, again, we kind of have a pretty cool star, right? It's not a very warm one. As you work your way to the left, you're going to see the temperatures increase, but also the luminosity increases with it. So the hotter a star, the more luminous it is. Now, these units along the luminosity here, this y-axis right here, they're kind of interesting. Notice their powers. Like this is 10, this is 10 to the power 2, which would be 100. This is 10 to the power 3, which would be 1,000. What that means is for stars like right here, I guess, like this guy right here, at 10 to the power 3, that means that star is 10 to the power 3 times brighter than our sun. Remember, 10 to the power 3 is 1,000. That star is 1,000 times brighter than our star. Crazy, right? Imagine if that was where our star was. We'd all go blind. It'd be so bright. It'd be insane, right? So again, in the grand scheme of things, our star is actually pretty dim and pretty cool and pretty boring, to be honest, right? Not really all that special. Now, one other thing to mention about this is anything in here that's in the darkness, just for whatever reason, just by the way stars work, there don't appear to be stars that ever form in those regions. So for instance, it doesn't really ever happen that you have a 30,000 Kelvin star in terms of temperature, so a really hot star, but a relatively low luminosity. There are exceptions that form in this little cloud called white dwarfs. We can talk about white dwarfs in a second. They're kind of outliers on this. Other outliers include the giants, which kind of just branch off from this at some point, as well as the supergiants, which are kind of the wild card. They're just very bright stars that could be basically any temperature. We got this star over here, Betelgeuse is what it's called. That's a pretty well-known star. I believe it's found in Orion's belt. I could be mistaken. I'll come back to you on that one if it's not. But it's kind of unusual in that it's a relatively cool star, but it's also very bright. So definitely an outlier in the whole scheme of things, right? Anyway, moving on from there. HR diagram, you don't have to memorize it, but you do need to know how to interpret it. That's basically all I'm looking for. This is interesting. It's a life cycle of a star. Stars actually go about a different life cycle depending on how massive the star is. So stars are all formed from something called a stellar nebula, which is basically just a spinning cloud of gas, like absolutely huge, about the size of a solar system, this huge cloud of gas. And as soon as it starts getting a spin to it, which can just happen just by the gravitational interactions between all the gas particles within there, as soon as it gets a spin on it, it actually starts to flatten out like a piece of pizza dough, right? So think of like a chef spinning a piece of pizza dough. The pizza dough, as soon as he spins it, flattens out. When it flattens out, it all wants to kind of form together in the center as a star. Now, depending on how much matter was in that stellar nebula in the first place, that big cloud of gas, it could form a relatively small star like the sun, or a pretty massive star like some of the crazier ones like Betelgeuse, right? Now, depending on what size the star was when it forms, that actually dictates what its life cycle is going to be. So it all starts right at birth. What is that life cycle going to look like? That's decided when it's born. If the star is relatively small, like about the same size as our sun, eventually, after billions of years, as it lives its life and finishes burning all of its hydrogen and turning that into helium, it'll eventually expand and become something called a red giant. Now, a red giant, it doesn't have any more mass than our star does. It just expands out, so it becomes a lot less dense, and it grows and grows and grows. After a red giant starts exhausting its fuel even further and completely runs out, it implodes on itself and then blasts outwards into something called a planetary nebula. This happens through a process called a nova, not to be confused with a supernova. A nova is just basically where a star dies, crumples in on itself, and then blows up outwards. It's an explosion, but not a super massive one in the whole grand scheme of things. This shoots a bunch of gas and a bunch of rocks and stuff, whatever happened to have been trapped inside that star. It shoots them outwards to form something called a planetary nebula. Notice the word nebula again. It kind of basically means like a space cloud is a really simple way of putting it. The reason this one's a planetary nebula is because after a star dies, there's a lot of higher up things on the periodic table that form, things like carbon, things as far as iron, or even further than that. Those things are actual like solids at standard temperature, so they'll rather form into like rock chips, whether it's asteroids or whether it's planets themselves. So this planetary nebula basically forms where you can end up having a solar system with actual planets form after that. Now, this is something I'm not really super impressed with this diagram on this, because really what happens is after a planetary nebula, you can actually end up going back to this stage right here. A planetary nebula can die, like, and form out like this, and then end up crumpling back in like a pizza dough back to a star, and the cycle begins again. But eventually it runs out of fuel, you know? So eventually what will form is something called a white dwarf. Oftentimes that'll happen after only one explosion. Sometimes it takes a few. But the bottom line is a white dwarf is basically just a really, really, really small, dense, cool star, right? So it's a star that's more or less exhausted its fuel, but it's still like got enough mass to it that's producing heat. It's just not producing very much heat. And if we go back, or sorry, much light, I should say. I was gonna say, if we go back to this white dwarf thing, white dwarfs, they're warm, like warmer than our star, they're just really dim. So my mistake, they're not cool, I should say, they're just not very luminous. Now, in enough time, a white dwarf will eventually stop producing very much light at all, and it'll cool down and go to something called a black dwarf. Now, black dwarfs are theoretical. We don't actually have enough time that has passed in the age of our universe to have produced any of these yet, at least not to our knowledge. But it is theorized that white dwarfs will eventually simmer out just like a candle that's been burnt out and become a black dwarf. Anyway, that top row, that's just talking about like a relatively small star. If we're talking about a more massive star, its life cycle is a little bit more violent. A massive star will eventually turn into what we call a red supergiant. Now, this actually happens a lot quicker than what it does for a smaller star. It seems to be that the more massive a star, the quicker its life cycle actually gets processed through. So it's got a shorter lifespan if it's more massive. Bottom line is, though, it turns into a red supergiant, and because it has so much more mass, when it implodes on itself, it actually forms something called a supernova. Now, a supernova is nothing to joke about here. It's like a lot crazier than what a planetary nebula would be from a nova. A supernova is so bright, it can often emit more light than the rest of the galaxy that star was in combined. These are ultra, ultra bright. We've actually been able to spot supernovas happening in different galaxies, which, if you understand the distance between us and another galaxy, that is mind-blowing that we're able to see that. That's just how bright that is. If a supernova were to happen to any of the stars that are nearby us, I would be not surprised to say that would pretty much brighten up the night sky. Like it would be easily, I would say, as bright as the moon. I could double check on that one for sure. But they're saying if a supernova were to happen near us, there'd be some crazy consequences. Now, even if a supernova were to happen not near us, like they are actually expecting it to happen to that Betelgeuse star that I mentioned before, it would still be very, very bright. Matter of fact, something that's that far away, it could be so bright you could even potentially see it during the day. So it would there'd be like a star visible in the day. That's how bright it would be. Kind of cool. But anyway, after a supernova, there's two possible things that can happen. It can form something called a neutron star. We don't really need to know too much about those. They're just an ultra, ultra, ultra dense, star that forms right at the center where the supernova was. But if it's even bigger than that, something more interesting forms. It forms something called a black hole, which is just something that is so dense and has so much mass packed in it that not even light can escape its grasp. Anyway, that was a long ramble on the life cycle of a star, but it's interesting stuff. And you are expected to know the difference between the life cycle of a small star versus a big star. Anyway, speaking of black holes, we unfortunately don't need to know too much about this, but it's still interesting to talk about. Now, black holes, they're not very well understood, but they're generally thought as being an object with such high mass that even light can't escape the gravitational pull. So imagine that, like light can't escape it. So when you see a black hole, it's not literally a hole in the universe. It's just some object that is so massive, it's got so much weight to it that not even light can escape its surface. That's crazy, right? Now, here's another mind-blowing fact. There's a supermassive black hole at the center of every known galaxy. And that's just the thing that everything in a galaxy orbits around. Black holes don't have to just be in the center of a galaxy, though. They can be in other places as well. But yeah, still very interesting. Now, these photos here, they're quite fascinating because up until a couple of years ago, we've never actually been able to process an image of a black hole because they're usually obscured by things that are orbiting around it. Like there's so much stuff swirling around it that you don't actually see the black hole itself. But there's a scientist, I believe her name was Katie Bauman. She actually discovered basically how to program a computer to spot and analyze and find these. And sure enough, she got an image of one. This photo that you're seeing on the left here is the first ever processed photo of a black hole. So pretty cool stuff. Anyway, moving on. Speaking of galaxies, we've talked about galaxies a couple times now. Galaxies are just insanely massive groupings of billions of stars. So when you see a galaxy, like a spiral like this or whatever, notice that there's billions of stars in there. That's insane. There's more stars in a galaxy than there are people on Earth. Crazy. Now, our galaxy, which is called the Milky Way, is a pretty massive galaxy in the whole grand scheme of things. We're actually quite fortunate what kind of galaxy we live in. It contains about 150 billion stars. So it is a really, really, really big galaxy in the grand scheme of things. Now, another thing to know about galaxies are there's three main broad categories. There are spiral galaxies, which are obviously named because they have a spiral shape. There's elliptical galaxies, which are basically just galaxies that look like a big oval kind of shape. And then there's irregular galaxies. They're kind of a little bit more of the wild card here. You can get some galaxies that look pretty strange. Like this guy over here, it just kind of looks like a big smudge. There's not really much rhyme or reason to it. But still, there's billions of stars in there. It's crazy how those form. Spiral galaxies, which is what the Milky Way is, certainly are a lot more interesting to look at for sure. But anyway, moving on. Now, away from galaxies, we need to talk, of course, about the universe. The universe is everything that exists in our reality. Everything that you can even think of, all the space in anywhere, all the light anywhere, all the energy everywhere. That is what the universe really is. The universe is not just matter. The universe is space itself. It is everything, everywhere. Now, our universe is the only universe that we know of. It's theoretically possible, however, there are others. Keep in mind, I should have mentioned on the galaxy slide, there are billions and billions of galaxies in the universe, like billions of them, if not even trillions of them in the universe. But we only think we have maybe one universe, right? So we don't actually have any way of proving that there's anything outside of our universe. So again, there are at least 100 billion galaxies in the observable universe, but that's just what we can see. The observable universe is just what we can see in a certain direction in all different ways. But we know just by how the universe must have formed that there must be stuff outside there that just hasn't had enough time for the light to get to us yet. That would be the total universe, or the full real universe. The observable universe is just the stuff that we can see. Crazy stuff to think of here. Obviously, there's not much else we can say about this. The human brain is not even wired to understand numbers like 100 billion, at least not in any meaningful way. It's hard to imagine what that really looks like, but it's mind-blowing nonetheless. So for practice today, I want you to try page 391, questions 1 to 7 and 9. And remember, if you need any help, make sure you are popping into the Zoom and asking. Anyway, best of luck.